Hey guys, BuildZoid here, and today we are going to be taking a look at the Gigabyte Z490 Aorus Xtreme motherboard. So this board is Gigabyte's flagship for Z490. It's $800, and well, that alone is, in my opinion, a good enough reason not to buy it, regardless of how cool it is. But it is a really cool board, so yeah. Like the thing is, it's kind of like with a board like this, Gigabyte really gets to sort of show off what they're capable of. The downside to that is the price is just not real, like not okay in my opinion at all. But anyway, let's just get into it. So starting off with the rear I/O, we've got the everything solution here, where you've got 10 gig of Quantia LAN, 2.5 gig Intel LAN, Thunderbolt 3 built in, Wi-Fi 6, HDMI output for the iGPU. Any of the available leftover space has been filled up with USB ports. You've got Q flash for updating the BIOS without a CPU installed, clear CMOS button for clearing the BIOS settings. Then on the board itself, we have, of course, dual 8-pin power connectors. And actually, on Z490, having more than just the single 8-pin is actually useful because the 10900K can pull absolutely ridiculous amounts of power. So, yeah, I don't actually have a problem with this having dual 8-pins because the funny thing is, 8-pin, like, having dual 8-pins can still be used as an 8 plus 4-pin configuration. But also you can just use it as an 8 plus 8. And normally if you have a power supply that supports 8 plus 4, it also probably supports 8 plus 8. So, um, yeah, anyway, but the only time you'd need to plug these in if you're like very heavily overclocking a 10900K, which is well, the thing is like I feel like technically yes, the board is kind of designed to do that, but I at the same time I feel like if you're very serious about like overclocking a 10900K, you might just get an Apex instead. But I guess maybe if you want, like, it depends. Make up your own mind. Like, I do have a review sample of this board from Gigabyte, so obviously I'm gonna be going to town on this thing. But yeah, this is a really hard to justify motherboard in my opinion in terms of just like it's so damn expensive. I wish they made like a stripped down version without like the 10 gig or the Thunderbolt or the Wi-Fi. Also, the board comes with all of this like metal heatsink work. Well, actually, it's not even heatsinks, like just metal covers over all of the motherboard to make it more aesthetically pleasing to normies. Personally, I love the look of naked 90 amp smart power stages, but most of people don't find those very appealing. But yeah, if they could ship this without the heatsinks and just the backplate, I'd be totally cool with that. Especially if it would make the board significantly cheaper. Fortunately, there'd probably be such a low volume of people, like such a low number of people interested in buying a motherboard without any of the extra frills, that they're never gonna do that. But I think it would be really cool because this board, like the thing is, Gigabyte's like, well, if you want the extreme, but like just the overclocking parts of the extreme, then you should just get a master. But it's like, but the master doesn't have the 8-layer PCB or the SMT Dimm slots. So that's not a fair comparison. Anyway, moving on, we've got the postcode, which you do get on the master. You get a bunch of voltage read points right here, and Gigabyte actually has voltage read points for every voltage that you can adjust in the BIOS, at least as far as I can tell. I think maybe VTT DDR might be missing. Like some minor things might be missing, but you even get like the PLLs are available for measurement, which not all motherboards that have voltage read points will include the various PLL voltages, which is pretty cool that Gigabyte has those. This button up here is unfortunately not safe boot. It's labeled OC ignition. It just preloads an overclock profile from Gigabyte. I recommend you just kind of ignore that exists. That's another thing that's just kind of taking up unnecessary space on this amazing motherboard, in my opinion, and making it extra, like adding to the cost. Probably less so than like the 10 gig LAN or or all of the aluminum that covers the motherboard, but definitely not something I'm like, if that went missing, I wouldn't care at all. Anyway, power button, reset button. And then we've got right-angled connectors for everything, including the 24-pin. Now, the board is EATX, which the right-angled 24-pin, right? Because that's where your ATX board's supposed to end, like by the actual mounting hole. And, well, it doesn't end there. And then you have the right-angled 24-pin, and Gigabyte does sort of recess it into the board a bit, but nonetheless, that 24-pin is going to be sticking out of the motherboard to the side. So case compatibility with this board, especially in terms of like cable management, is going to be Something to watch out for because, yeah, that 24 pin is just going to stick way out of the board. Anyway, so then we've got like a bunch of like right-angled connectors for basically everything except like this USB port right there. And then at the bottom of the board here, we get the dual BIOS chips. So there's your backup BIOS chip, main BIOS chip. You've got LEDs to indicate which one's active. Unfortunately, the LEDs are right next to each other, so if you just have like the board sitting, like you won't be able to tell which one's running just at a glance because the LEDs are basically within, well, they're right next to each other. They were a bit more spaced out. I'd prefer it, but yeah, like, well. You need to have an indicator at the very least, but these are kind of, well, actually the funny thing is there are dual BIOS Gigabyte boards which wouldn't give you an indication, but those are like pretty old. Actually, wait a minute. I think the B550 Master might not indicate which BIOS it's on. So yeah, that's obnoxious, isn't it? But anyway, yeah, here you do have, at least you have indicators, because without them that gets pretty annoying. And then, of course, because Gigabyte themselves acknowledge that their automatic dual BIOS system is stupid and annoying when you're overclocking, their high-end motherboards that have the automatic dual BIOS also have these two lovely switches over here. One of them disables the automatic dual BIOS functionality. The other one allows you to select which BIOS chip you're on. And if you're buying a high-end Gigabyte board that has these two switches, I strongly recommend the first thing you do when you pull the board out of the box is you go into the manual, you figure out which of the switches puts the board in single BIOS mode, and you put the board in single BIOS mode so that you don't have to deal with the automatic BIOS switching. Because if you're tuning memory or something and you fail to post like 3 times in a row, it'll switch BIOS chips and you'll lose your profiles unless you're saving them to like a USB stick. It's very annoying. Trust me on that. Well, anybody who's used a Gigabyte motherboard can tell you about how annoying it is, right? Because even Gigabyte themselves will give you the freaking switches to disable it. I honestly don't know why they bother. Like, most other board vendors will implement dual BIOS as just 2 BIOS chips and a switch to choose which one is active. And then there's Gigabyte where it's like, yeah, so there's automatic software dual BIOS, and then we give you the option to turn that stupid software functionality off. It's like, you could have just not had the automatic part in the first place, you know? Like, just saying. Like, this is like having an automatic car transmission that's so bad that there's a manual override for it in the higher end, you know, specs of the car. It's like, are you kidding me? Just make a manual if you can't make a good automatic. Anyway, so yeah, you do have the dual BIOS switches. So really the only thing in terms of overclocking features on this motherboard that I think is missing is a safe boot button, which is really annoying in my opinion. For a motherboard this expensive, like, you would want a safe boot button, especially since this is a Gigabyte motherboard, and Gigabyte BIOS along with like Asus BIOS, and actually ASRock BIOS is pretty bad about it as well. I think MSI is like the only motherboard vendor that has like consistently has motherboards that will just give up very, very quickly if you punch in bad bad settings. But like the rest of the board vendors, you punch in bad settings, and especially on the Intel platforms, like they will get stuck in a boot loop basically forever, or potentially just get stuck on one postcode and not, like, they won't even loop. They'll just get stuck on a postcode and just stay there forever. Which is really annoying because, yeah, the board won't recover from any kind of failed overclocked. And, like, on some generations, it's better with some vendors, but generally it's terrible. And Gigabyte generally, yeah, it's not great about this. So basically, this is the kind of board where you're going to be doing a lot of save profile, fail to post, clear CMOS, load profiles, start over. So exactly the kind of scenario where a safe boot button is most useful. Yeah, so I'm kind of sad that that's not the case, but yeah, like, you know, you have the sort of the bare minimum in terms of overclocking features, which most of that's just the postcode. Like, that's the really important one. The dual BIOS is nice, and then the buttons are just like, well, if you're a really lazy test bench user, the buttons are, of course, nice to have. Anyway, so let's get to the power delivery, because there I don't actually have any I don't actually have any complaints for the power delivery here. So Gigabyte for this board has given us the biggest VRM that they make for Z490, which is a given. And so this right here, and they do include an iGPU phase, which, as you can tell from the HDMI port on the rear I/O, So you can actually use QuickSync. There are some higher end motherboards, especially from actually there's quite a few Z490 motherboards that won't bother with including an iGPU phase. And well, if you don't have an iGPU phase, you can't have QuickSync because QuickSync requires the iGPU to be functional. And if you don't have iGPU power, guess what's not functional? So yeah. Anyway, so this does have an iGPU phase because the board has to do everything. Otherwise, how would it justify the $800 price tag? And then down here, we've got VCCSA. And you might be like, why are you highlighting VCCSA already? Well, VCCSA is controlled by the same controller that does vCore, so it just makes sense to highlight both of them at the same time. And the rest of this VRM is just vCore, which is one of those 8/16 phase setups using the ISL 6617 doublers. On the back. So the controller is that chip right over there. That's an ISL 69269, the latest and greatest high phase count controller you can get from Intersil. It goes up to 12 phases total. Here it is running, and it does triple output, which is actually kind of like really supporting up to 12 phases is really cool. The fact that it does triple output is kind of the more unique feature for sort of high-end controllers. They normally only go up to dual output, but yeah, this does triple output. So here it's running as an 8+1+1, which means one of the plus ones is the iGPU, the other plus one is the VCCSA, and then the 8, of course, is vCore. The 8 then goes on the back of the board into these chips right here, and those are all ISL 6617s, and those are doublers from Intersil. Now, these are kind of cool because unlike, well, there's a lot of different types of doublers, but these are basically the smartest doublers you're going to see because these can both interleave and run synchronous mode. So in interleaved mode, they actually give you a higher phase count, which improves like your input ripple, and well, that's about it. It improves your input ripple and improves your efficiency slightly. And then they have synchronous mode where they'll actually not interleave the phases at all. But what's cool with these is they monitor the current going through each power stage that they're controlling. And so even if you're in synchronous mode, the thing is these do PWM pulse extensions. So in synchronous mode, these will still current balance the power stages that they're in charge of. So you can actually have sort of like an 8-phase VRM, but with 16 power stage current balancing, which gives you slight, like your input ripple is going to be somewhat worse due to the lower phase count, but your efficiency is actually going to be closer to that of the like 16 phase setup than not. And the reason why synchronous mode is included on the ISL 6617s is because in synchronous mode you get a transient response advantage because you don't get a pulse width length limitation, because obviously if you're interleaving you actually can't set a PWM pulse higher than like 50%. Not that I've ever actually seen a VRM use a like very like such a long PWM pulse. Like I've not seen 100, like anything approaching 100%, or even going like past 50. Like I've not seen a pulse that long ever. But at the same time, there might be some scenario that I've just not run into in my testing. And there like other doublers don't bother with that kind of functionality at all. Like the option to go up to 100%, just other doublers don't do that at all. Yeah, so the other idea, well, the sort of the thing is, like, Intersil themselves suggest using the synchronous mode as a sort of fast transient response mode for the VRM, where it's optional, where it kicks in when you need it. But most motherboards are either synchronous or interleaved, and they don't go between the two modes. That's just not a feature that most motherboard vendors bother with enabling, which I don't know. I think that's kind of lame because you could kind of have well, the thing is, having both modes active, like having the board dynamically go between the two modes, just makes the design a lot more complicated. Because the reason why putting the power stages, like running the power stages synchronous, gets you better transient response is not really so much from the pulse extension. It's because your inductors end up in parallel, and so you get half the inductance for your phase. Which gives you twice as much current slew rate. So, yeah, anyway, these are pretty cool doublers, and I'm going to assume that Gigabyte's actually running them in the 8-phase configuration here. So, Yeah, because the inductors that they have on the board are 300 nanohenries, which the thing is like running them in parallel, you ultimately end up with like 150 nanohenries effective inductance, which is really like that's low, right? And that you can see that on the iGPU phase where it's like, okay, well that one doesn't have a doubler, so that one's on a R15 inductor, which is 150 nanohenries. Um, Anyway, so that's kind of the thing is if you also have really low output inductance, then your input ripple gets really bad. So that's kind of like there's trade-offs to this. All for like there's a lot of trade-offs to every sort of design decision that you can make. Anyway, so that's the control scheme here, and of course the doublers add a very slight delay to the PWM signal. It ultimately doesn't really do much of it. Like it doesn't make enough of a difference to the transient response that you can't like design it away in other ways. Um, and Gigabyte's the solution for getting better transient response on Z490 is wait, are we gonna go? Yeah, let's do the capacitors. Hey, so is these capacitors right here. And then on the back of the board, we've got all of these capacitors in the socket, and then also these right here. So these are all Panasonic's, and well, technically we also have them on the input of the VRM, but like they're not the same. Well, they're still tantalums. Like, man. See, this is the thing. I don't like things that I normally talk about in PCB breakdowns, easy, because I already like talked about them multiple times, so I know how to like transition in and out of those, but then it's like, oh, Gigabyte's doing something weird with their capacitor configuration. Which actually this isn't really that weird. Like tantalum capacitors aren't new or unique. Like it actually if you go far back enough in time, there used to be a lot of motherboards that would go for tantalum capacitors for their output filtering, but they're expensive, so they stopped being very so over time, motherboard manufacturers stopped using them because it's like, well, we could make we could, get the boards are cheaper to make if you don't use these. But yeah, like basically I did some testing for Gigabyte and I was like, hey, maybe if you want better transient response, just throw a bunch of SMD capacitors on the output. Because the important thing with these is and so anyway, like these are pulse caps from Panasonic, and they're tantalum polymer capacitors, and we obviously have somewhat like I'm gonna assume these are like 2.5 or 4 volt. These are gonna be 2.5. So we have like 2.5 volt pulse caps for the output filter of the V-core as well as the memory. And then on the input we have 16 volt pulse caps because Gigabyte decided that this board's like input filter is actually completely ridiculous by Gigabyte motherboard standards. Like we've got these 4 regular through-hole aluminum polymers, these two more aluminum polymers right there, and then all of those tantalums as well. So that's actually like that's pretty unique for a Gigabyte motherboard because like especially if you compared this to like the Z390 Xtreme, like that board has I think 3 16 volt like 3 through hole 16 volt capacitors in total, and that's it. Like there's no extra other capacitance. And then for Z490, Gigabyte just kind of like this is basically like I think the idea here is basically they want the lowest possible input ripple, the best possible transient response on the output. And well, this is one way to brute force both of these, is just throw more capacitance on the input and throw better capacitors at the output. And that's basically what the pulse caps from Panasonic do. But and the main reason that, as far as I'm concerned, that they're doing this is because I did some testing for them at the end of which I was like, yeah, maybe just add some SMD caps to the output. And the reason why I like specifically SMD cap, well, the funny thing is, so SMD caps, it's not so much about the fact that these are a like surface mount device, because that's what SMD stands for. It's about the actual sort of rectangular molded package that these come in, because you can technically get your regular through-hole CAN capacitors in a SMT package as well, where they basically just take the legs and flatten them out. And those still suck. So, well, it's not that they suck, but like basically the reason why these are being used to improve the transient response of the motherboard is because this style of capacitor packaging has much lower ESL than the regular CAN packages. and ESL is basically parasitic inductance in series with the capacitor, and it basically means that when there's a very rapid voltage change on the power plane, well, or more like when you need to quickly change the current flow into the capacitor, you can't because there's a bunch of inductance in the way between the actual capacitor and well, so like basically the problem is like so if you have a load insertion transient, you suddenly need to pull a bunch of current out of the capacitors, and if you have a bunch of inductance in between the capacitors and the CPU, which is where the ESL comes in, you're going to have a voltage dip, or a bigger voltage dip than if you had less ESL. And similarly, if you're trying to dump energy from the input filter from the output, like from the inductors into the output filtering capacitors on a load release transient, then having a bunch of inductance on the capacitors basically means that it takes more time to get that energy into the capacitors, and so you get a higher voltage spike on the output of the VRM. So by adding these, it's not so much that these have like more capacitance or anything. They're just better at absorbing energy, like soaking up and releasing energy faster than your regular through-hole capacitors. So that's the idea behind having these on the motherboard, along with all of the through-hole caps. Like, I'm honestly surprised that the board is $800. I don't get why they didn't just get rid of all the through-hole caps. Like, I'm really not sure why they didn't do that and just replace them entirely with the pulse caps. Because if you look at the Z490 ITX board from Gigabyte, that is all pulse caps, and they're great. And well, we'll see if my theory that I can't wait to get the transient response measurements for these boards, because with Gigabyte is just doing a lot of cool things with the pulse caps on their Z490 boards, and the ITX is basically the entire output filter is just pulse caps. And then of course we have this board here where it's like we have pulse caps and then the through holes, and it's like I don't think the through holes are necessary. Yeah, and also they've jammed them right into the socket, which is kind of interesting because, jamming caps right into the socket is kind of interesting because you'd think that having a bunch of multilayer ceramics is probably better, because multilayer ceramics are even lower ESL than your tantalum polymers in a molded SMD package, or aluminum polymers in the same style of package. But the thing is, I'm pretty sure with multilayer ceramics, you actually end up with the impedance of the capacitor, like the impedance of the capacitors on the motherboards ends up being so much lower than the impedance of the CPU socket that at some point, more multilayer ceramics on the motherboard just doesn't do anything. Because you're no longer limited by the impedance of the capacitors, but by the impedance of the socket. So, yeah, that is one thing I'm definitely wondering about, because Gigabyte isn't the only vendor to have redesigned their capacitor configuration on Z490. So, yeah, that'll definitely be interesting. They've also whacked pulse caps on the input to minimize the ripple, pulse caps on the output to improve the transient response, and then they whacked a bunch of them onto the memory as well. I don't think those will actually do anything. Like, I've done some checks for memory. Well, so I've done some measurements of memory, sort of transient response, and the thing is, memory just isn't very difficult to power. The biggest transient you have is the refresh cycle of the memory sticks, and unfortunately, that transient, like if you measure it on one of the really small capacitors that's directly attached to an actual pin for one of the memory chips, the transient looks really bad. But if you measure it from any of the sort of larger capacitors that's just generally bypassing the entire memory stick, you don't see much of it anymore. And so I think doing this on the motherboard just isn't really going to do much of anything, because it's not again, you just run into the issue of there is impedance between these capacitors and the actual memory chips that is far too great to be affected by the fact that now you have a very low ESL, very low ESR capacitors added to the output filter of the memory VRM. But it's not like they hurt anything. And it is cool that they've done that. It's just, yeah, I will be very surprised if that leads to better memory overclocking, but we'll see. That is definitely something I plan to test. Unlike the VRM thermals, because now that we've talked all about the capacitors, we can get back to the actual power stages, right? And for these, Gigabyte is, of course, using the very best that Intersil has to offer, and that is the ISL 99390. These are 90 amp smart power stages, and they are using them absolutely everywhere. You've got one in iGPU, then of course you've got every single phase in vCore has one of them as well, and then VCCSA has another one as well. So VCCSA is extremely overkill on this motherboard because you've got a 90 amp smart power stage for a rail that, like, well, I've never actually measured VCCSA power, but by Intel's own specifications, it's like a 10 amp rail. And yeah, so that's probably not gonna like you can like that rail regularly works just fine with discrete MOSFETs. So I'm actually really surprised that they're going all the way with a 90 amp smart power stage for this, but I guess it was more to just avoid having to include a driver, and at this point they already had all these other 90s, so it was just like, just whack on one more for VCCSA. It's not really going to change the cost of the motherboard. It's way too expensive already. Anyway, so these are called smart power stages because unlike regular power stages, they integrate very accurate current monitoring, also temperature monitoring. That's not any more accurate than usual. It's like just basic temperature monitoring. And they also include a bunch of safety features like short circuit protection, over current protection, over temperature protection. And they're also ridiculously efficient compared to like past generations of power stages. So yeah, these are literally the best power stages Intersil has to offer. There's a lot of Z490 motherboards actually using these, like Gigabyte's Xtreme, the Z490i Ultra from Gigabyte, the Master from Gigabyte, the Unify from MSI, the ITX Unify from MSI, the Ace from MSI, the Godlike from MSI. So yeah, for high-end boards, these are very popular because if you're using an Intersil controller, this is basically the best power stage you could pair it with. And still have like full support from Intersil. Because the thing is, the reason you don't see like an Intersil controller with international rectifier power stages is because if there's any kind of design problem, you won't get support from either of the manufacturers because they'll just be like, "Nah, you're not using our you're not using our controller. We're not going to help you with any design issues." And if you go to Intersil, it's like, "Oh, you're not using our power stages? Well, too bad." It's like that's why it's not working the way it's supposed to. It's because you're not using our power stages, even though they technically should be intercompatible. Like the PWM signal, there's a standard for the PWM signals that the power stages should support. But yeah, if you want any kind of design support, like you're not gonna mix components. So for Intersil controllers, this is the very best you can get. Anyway, the end result of having all of these phases and these very high-end 90 amp smart power stages, which one thing I forgot to mention is that 90 amp nominal current rating is a bit misleading because technically if you compare the actual performance curves of the 90 amp power stages to like 70 amp power stages, 70 amp smart power stages, the funny thing is there are some 70 amp smart power stages that really aren't that impressive compared to like other 90s and 70s. But then there's 90s and 70s that basically perform the same. There's also 60s that perform very similarly to 70s, which basically just like that nominal current rating is basically pretty useless. And I wouldn't pay too much attention to it because within the part of the performance curve that you actually care about for day-to-day, for practical applications, you're not actually going to notice any real performance difference between like a international rectifier 70 amp smart power stage and an Intersil 90 amp smart power stage. So anyway, but these are still ridiculously efficient power stages. Like they don't get that 90 amp nominal current rating for no reason. It's not like it's made up. It's not a practical real world usage scenario rating. Anyway, so for 1.2 volts output voltage, 500 kilohertz switch, and that's a horrible 500 kilohertz switching frequency. The VRM is going to have roughly the following efficiencies for 200 amps output, which is very like a 10900K will blow right past that. If you're pushing a 10900K, 200 amps is not a problem to do. The VRM will produce about 15 watts of heat. You literally do not need a heatsink while pushing this much current, because that is literally less than 1 watt of heat per power stage. And at around 1 to 1.3 watts per power stage, you can actually get away with running power stages naked, because between, like, the thing is, like, the PCB itself acts as a heatsink, and this motherboard does use an 8-layer PCB. Then, of course, you have the inductors, which are basically just giant lumps of metal, so those make pretty decent heat sinks themselves. And then it's not like the power stages don't have a decent amount of surface area to themselves as well. And so, basically, the VRM, if you're not pushing, like, with this large a VRM, and low enough heat outputs, the VRM is actually perfectly capable of cooling itself without any help from like a heatsink or anything. So, and that's very much the case. At like 200 amps output, you don't need a heatsink on this at all. At approaching 300 amps output, you still don't really need a heatsink unless you have very high ambient temperatures, in which case I'd be wondering about how on earth you're cooling the CPU. Because, yeah, the VRM at 300 amps output will only be producing about 23 watts of heat, which is still within that sort of up to 1.3 watt range. Now, admitted, like, I actually did a test with this board where I ran Prime 95 on it for 2 hours, no VRM heat sinks, and in a 21-degree room, and ultimately the VRM temperature at the end of those 2 hours was like 93 degrees right here. This part of the VRM was actually sitting at around 80, because there's a lot more 12-volt power plane hanging out right above that, and also there's just less power stages in this area, so like the heat density here is somewhat lower. But yeah, this area was like the hottest power stages in this area were a little over 90 degrees, and I was running, I think, 360 watts of power into the VRM, so not quite 300 amps output, but approaching it. And we were still well below 100 degrees on the power stages. So, yeah, like, this VRM, like, they literally could ship the board naked. Like, especially because that was on an open-air test bench with 0 airflow. If you had this in a case with any amount of airflow, it would be completely fine. Hell, if you had, like, a fan for cooling your ridiculously overclocked B-die memory, right? Like, your VRM would be cooled adequately by the wash-off from the memory sticks. So, yeah, anyway, the VRM on this is ridiculous. And there's a bunch of boards, actually, with a similar VRM configuration to this. Like, the Master basically is this VRM without 2 power stages, and ends up roughly in the same scenario where it's like, yeah, you don't really need a heatsink. Anyway, going past 300 amps to 400 amps output, where now you're looking at, like, sub-zero cooling. The VRM will produce about 34 watts of heat, so now the heatsink starts technically serving a purpose. The only issue is, if you're on sub-zero, you're probably not running multiple hours of Prime 95. So, still not a real, like, useful real-world usage scenario. But hey, if you wanted to run Prime 95 at, like, what is that? That's like 1.2 volts. Yeah, like 500 watts of power consumption, Prime 95. The VRM might actually need a heatsink then. Like, it'll be fine. Like, 34 watts of heat is not that hard to deal with a, like, especially considering the heatsinks this board comes with. Like, that's a lot of surface area. Right? Like, that is a hell of a lot of surface area. And also, Gigabyte is using some very nice thermal pads from Lyard. These are 7.5 watts per meter Kelvin, if I'm not mistaken. And they're also extremely soft. So, that's a good thing, because they, get really good contact with the actual power stages and the power plane. The funny thing about power stages is that actually the packaging material is so, like, relatively high thermal impedance. So if you want to properly sink heat from these, you're actually doing, like, it's better to sink it from the 12 volt and the, like, switch node of the VR, like, from the 12 volt power plane and the switch node of the VRM, than it is to try sync the power stage directly, because the black epoxy material is actually relatively high thermal resistance compared to the PCB. And of course the power stage is just soldered to the PCB, so the solder is pretty thermally conductive. Yeah, so, like, the heat sinks on this board are completely ridiculous. So yeah, if you for some reason did want to have a 500 watt CPU, like, this board would totally handle that. It's just completely impractical for any kind of, like, you'd literally need to be probably running the CPU at like minus 50, maybe lower, in order to like hit this kind of current draw. Um, and even like 400 amps would probably degrade your CPU pretty quick. You might want to be aiming at like a minus 100 instead of minus 50. Um, Anyway, going past that, say like for LN2 overclocking or something, 500 amps output, this VRM will only produce about 48 watts of heat, and 600 amps output, this VRM will produce only about 66 watts of heat. So basically, there is absolutely no scenario in which this VR, like there's no way a 10900K can practically overload this VRM. Well, I guess if you wanted to run Prime 95 on LN2, that might actually, but multiple hours of Prime 95 on LN2 would burn so much LN2. Like you probably couldn't do 2 hours of Prime 95 on LN2. Like if you had like a 30-liter DWAR, you'd burn through it in a couple minutes, I would assume, if you were pushing that much current. Like yeah, like there's just no scenario where you'd hit the limits of this VRM. So this is like adequate levels of overkill because they could literally ship the motherboard without heat sinks. And who doesn't like with a VRM this good, why wouldn't you want it naked in your system? There's just one issue with shipping this board with no heat sinks, the 10 gig LAN. Like 10 gig network, 10 gig LAN chips get pretty hot, so that actually would still need a heat sink. And it would probably not be that happy that the VRM's running, kind of warm. So, yeah. But the VRM here really doesn't need the cooling. Anyway, VCCSA, as I mentioned, is on a 90 amp smart power stage, so that's mega overkill. iGPU is on a 90 amp smart power stage, but it's not like people overclock their iGPUs or even really use their iGPUs that much, so that's not a concern either. For the memory power delivery, we're looking at the bog standard Gigabyte single-phase memory VRM that they've been using, I think, since Z170 is when they introduced this three MOSFET, where you have one high side, one low side, and two low sides, controlled by this chip over here, which that's an RT8120, and that's just been the same VRM for so long. 4C06N MOSFETs, and it's a single phase. And like the funny thing is on X99 they actually had significantly more substantial memory VRMs, but the thing is DDR4 is not hard to power. Like it just doesn't pull that much current. It also doesn't really have that nasty transients. So what's much more important than how you power your memory, which this is completely fine. Gigabyte's like it works. Like that's the reason why Gigabyte's been using it over and over and over again. What's far more important than how you power the memory is how you connect the memory to the CPU. And for that, Gigabyte here is using so we have an 8-layer PCB, which incidentally, fun fact, if you want to know how many layers oh, you can't see it. Oh, that sucks. Wait, can we see it on the back? Because it might be visible. Oh yeah, no, you can see it right here. So on Gigabyte boards, normally along the bottom edge somewhere, you're going to have something that looks like 4 squares next to each other. That has a number in it that'll give you the layer count. So yeah. You can also sometimes manage to see it in the actual photos on Gigabyte's own website. So you don't even have to you can potentially just look at the pictures Gigabyte has on the website for the layer counts sometimes. Not always, but yeah, they have a little layer count indicator down on the bottom edge. There's MSI also has that. MSI actually has it really obvious, and some high-end boards will occasionally highlight how many layers they have with some kind of layer count indicator. But anyway, this is an 8-layer PCB. Also worth noting, this actually uses the low-loss PCIe 4.0 substrate material. So also, that just means basically the PCB is more expensive and has lower loss for high-speed signals over long distances, which mostly just affects PCIe 4.0 because that runs at actually much higher giga transfers than memory does. So yeah, anyway, 8-layer PCB, and then we have a shielded daisy chain memory topology, which is why we can't see any of the memory traces, which is a really good thing that Gigabyte specified what topology it is, because otherwise, like, yeah, you can't see them because there's a great big ground fill over all of the memory traces. And the idea behind doing this is it prevents, well, it basically shields the traces from any kind of external interference. Um, and yeah, this is really popular on X570. That's, I think, the first platform that like you'd see daisy chains where you actually can't see any of the memory traces at all because they'd just be all hidden under great big ground fill like this. And yeah, now for Z490, Gigabyte is using this again. They claim that this board is capable of going up to 5,000 megahertz DDR4, but the thing is, Gigabyte is currently actively rolling out like lots and lots of BIOS updates that are significantly improving the memory overclocking, so this could very well end up going up. Um, so that's the thing is like right now claiming anything about Gigabyte's memory overclocking support is kind of too early because it's getting better very rapidly. So yeah, I think we'll know where Gigabyte's memory topology tops out in like a month or two. Um, Also, what's really neat about this board is it actually uses Smt Dimm Slots, which is another thing that should help with the memory overclocking capabilities. And the funny thing is, like, Gigabyte claims that 5,000 megahertz for their entire Z490 lineup, which the reason why that's funny is, or at least all of their 6-layer or higher layer count boards, um, and the reason that's kind of funny is because you'd expect the Xtreme here to actually be significantly better because it uses the Smt Dimm slots, which do lead to better memory overclocking, as well as having more layers. So that like there's a good chance this board might end up actually like basically what I suspect happened is like Gigabyte basically had the initial BIOS that they tested with basically just maxes out at 5,000 megahertz. And then if you want to go past that, like they still need to dial in the BIOS for the boards more specifically. So that's kind of the problem with like the memory to like well with memory there's two very important parts to it, the BIOS and the memory topology, and this has a very like strong memory topology, right? We've got a shielded 8-layer daisy chain, so this should work great in 2DIMM configurations. And then we've got the Smt Dimm slots, which should also work really great. And now it's just like Gigabyte's still polishing the BIOS, though 5,000 megahertz is already really high for a 4DIMM motherboard to start with. Also, we can see that this is on Smt Dimm slots because we can't see any of the memory pins. And the reason why the Smt Dimm slots help with memory overclocking is because they basically have better parasitics than your regular through-hole memory slots. So they have a slightly better integrity. For reasons that I'm not going to get into because, like, well, I'm probably going to screw up on the details. Yeah, Smt Dimm slots are pretty cool, and this isn't the only board to use them. Like the Dark series from EVGA did, or does. Well, some of it. The Z490 FTW also uses Smt Dimm slots, but the other thing is for Smt Dimm slots, you also have like Gigabyte was actually I think Gigabyte was the very first to do Smt Dimm slots with the X99 SoC Champion, or maybe they even used them before that. But with X99, the SoC Champion, like that board, they went absolutely crazy to try get it to clock memory as well as possible, and that I think is like the first board I can remember with Smt Dimm slots. I don't think they did a DDR3 board with Smt Dimm slots, but the X99 SoC Champion was first board with Smt Dimm slots. So it's really cool to see Gigabyte actually bring this back because this is like they did it on the Champion, and then I don't think they did it ever again until now. So yeah, I'm pretty excited about like seeing this, and it could mean like the combination of what Gigabyte has done here is this could end up being the best 4DIMM memory overclocking motherboard on Z490. And I'm saying could because again, it's not just about what you do with the hardware; it's also about what you do with the BIOS. And if the BIOS can't, because basically the BIOS has to configure like the CPU side of the operation so that the CPU can take advantage of the really good sort of hardware configuration of the motherboard for the memory. And, well, if the CPU's memory controller isn't configured to go over 5,000 megahertz, well, you're not going over 5,000 megahertz. It's really that simple. It doesn't matter if the board is capable of doing, 5500 or something completely stupid if the memory controller hits a wall at 5000. So, yeah. Anyway, like Gigabyte is doing some really cool stuff with the memory, and also the SMT DIMM slots are actually kind of the reason why we see the SMT pulse caps right behind the memory slots, because normally you can't do this because well, there's pins coming through the board, so you can't have capacitors sitting right behind the memory sticks. But again, I also don't think this will really do much, but I do want to try, like, I figure, like, I have a memory stick with the option to do, like, take oscilloscope measurements from it, so I do plan to do tests to see if this actually does anything, and just, I don't really expect it to do much. Anyway, I think that's it for the board. Right, we've done vCore, we've done memory, I've mentioned all the features. Like, yeah, basically, I really like everything in this area. Oh, including the dual BIOS. Yeah, so... But, yeah, so this is a really cool board, right? Like, you've got basically Gigabyte's best VRM, probably one of... And then Gigabyte's best 4DIMM memory layout, and I just kind of wish we could get those things at a cheaper price. Well, actually, the VRM on the Master is already good, plenty good. It's just like, I wish we could get that memory topology on the Master. With the SMT DIMM slots and the 8, like, well, honestly, maybe not even the 8 layers. Like, mostly just like the SMT DIMM slots could be really, really cool to have on a cheaper board. But yeah, and other than that, I guess Gigabyte would want me to mention that they're using like PCIe 4.0 compatible switches and a PCIe 4.0 clock gen and a like the board, like the reason why this uses the PCIe 4.0 low loss substrate is that they've actually designed the motherboard for, having PCIe 4.0 support once the 11th gen CPUs come out. But 10th gen doesn't support PCIe 4.0 at all, so not really like a useful feature as of right now, but still a really, really cool board. And yeah, like the main thing is just like, it's $800 Gigabyte. $800 is not an okay price for a motherboard, in my opinion. It doesn't really matter how cool it is. Like, it's not even HEDT. Like, it doesn't even have that many PCIe slots, right? Or more like PCIe lanes. The slot count is actually good. It's just like, yeah, more PCIe lanes, please. But that's not even Gigabyte's fault. That's Intel's fault. It's like, Intel, please make better CPUs. Because, yeah, we've got cool motherboards like this. For Z490. And then, like, the 10900K is cool, but it's like, I wish I could run 4-way off of it. Anyway, so that is it for the video. And yeah, in terms of what I'll be doing with the board, like, I've already done a no heatsink VRM thermal test, so I don't see a point in doing VRM thermal test with heatsinks, because, like, it doesn't overheat without it. Like, it doesn't matter at that point. If you can't, like, if it doesn't get too hot without the heatsinks, then it doesn't matter how hot it gets with the heatsinks, because it's not going to be hotter. But mostly what I want to focus on with this board is going to be like memory overclocking, because I'm really interested to see how that behaves. And then, of course, I'm going to be taking transient response measurements because, yeah, I do wonder about what all of those pause caps translate into in terms of transient response on the board. So, yeah, that's it for the video. Thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. And if you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below, where you can support me directly. That helps out immensely with the channel. Or there's the AHOC Teespring store, where you can pick up shirts, stickers, posters, the usual YouTuber merch. That also helps out a lot with running the channel. So, yeah, that is it for this video. Thank you for watching, and goodbye.